Yep.
Okay. So any questions on assignment 4 to start with?
I had a question about 5B.
Mm-hmm.
Like, I understand how it is subjective. I understand, like, I don't know how exactly to start showing it.
To show something is surjective. So, definition F from domain to range is surjective when for every y in the range there is x in the domain such that f of x is equal to y. So how do you show something is surjective? Okay, pick some arbitrary y in the range and find the x. Find some x in the domain such that fx is equal to y. Now you can't name y. Y just has to be an arbitrary thing in the range. So for our particular problem, in our particular problem, right, we have f from z cross z to z again. Right, so just let y be an element of z. So y is an integer. Okay, but you can't say anything about it. It's just an integer. Okay, find a pair. Right, find a b in z cross z, such that f of a b. Try that again. Is equal to y. Now, the answer you're going to get for AB is going to be in terms of y. Of y. The letters A and B won't appear. Just y. Okay, your answer is just going to be y. Like, for example, okay, so let's take a function f from the interval from 0 to plus infinity to the real numbers, defined by, well, no, sorry, from the reals to 0 to plus infinity. So a function f from the reals to the interval from 0 to plus infinity. Okay, defined by f of x equal to e to the x. Okay, show it's surjective. Okay, so you pick y in the range. pick y to be a positive real number, so something in the interval from 0 to plus infinity. Okay, which x goes to y? Which value of x gives you e to the x equals y? Pre-calculus, guys. Which x gives you e to the x equals y? Come on, guys. Which value of x gives you
ln(y).
natural log of y? Right? So f of the natural log of y is equal to e to the natural log of y is y. Okay, so the answer for x is in terms of y and y only. All right, so your answer in part B for AB is going to be in terms of y and y only. But there's several different possible answers. There's several answers possible because y is not, f is not 1 to 1. In this example, there's only one answer, the natural log of y, because the exponential function is 1 to 1. Does that help?
Yeah, I think so.
Yeah. If you want to email me your answer, I can check it for you. Make sure you're on the right track. Okay.
Okay.
That goes for everybody. I mean, if you're unsure about something, you can email it to me, and I'll give it a quick check for you. Anything else?
So for 5A,
Uh-huh.
pre-image of set 1, 2, 3, 4,
Mm-hmm.
we just find essentially ordered pairs that would add to those elements, right?
Mm-hmm. Yeah, and they're gonna have a familiar geometric form. They should look like something that you're familiar with.
Right.
Do the pre-image of 1, for example, the pre-image of the set containing just 1, and that should be, something that you recognize. And then the pre-image of the set containing 2 is, very similar to the pre-image of the set containing 1 geometrically. So you're just going to put all of those pre-images together. Pre-image for the set containing 1, the set containing 2, 3, and 4. عندي صف هلا ريما. ريما عندي صف هلا. خليني نفوتوا لجوا عندي صف. شو؟ خليني نفوتوا لجوا. تبي سامك هنا؟ عندي صف. Any other questions? Okay. So to finish up chapter 4, so we started last time talking about compositions of functions. So given two functions, f from domain A to range B, and function g from range B to, or from domain B to range C, you can compose those functions, and you call this thing g following f. Did I write that down? Yeah, g following f. From A to C, so defined as follows: g following f of x is g of f of x. So what this means, right here, what that means is that you have x in the domain A, and f takes x to something y and b, and then g takes y and b to something z and c. So that's what the blue means. It's these two functions put together, g following f. The definition of this is what what this represents. So it's a function that takes x straight to z. So in this example here, we just have some functions, defined with these bubble diagrams. Function f and the function g, and then we just show how the composition works. Now, again, like I was saying last time, it's important to get the notation right. G of f of 1, sorry, g following f of 1 is equal to g of f of 1. F of 1 is a. So this is g of a. G of f of 1 is g of a, and then g of a is w. Therefore, g of f of 1 is w. And you do that for all three domain elements, and you get this picture here. Okay, for g following f from A to C. And then this corresponds to, for the special case of functions from the reals to the reals that you used in calculus and pre-calculus and differential equations, the notion that you had of function composition back then is just a special case of what we're talking about now. So if you had, functions from the reals to the reals defined using, algebraically, or using those elementary functions, sines, cosines, polynomials, multiplication, division, addition, right? You can do composition as you used to do. So you can do g following f, f following g, g squared, which is g following g, g to the third, which is g following g following g, so on and so forth, right? And you can also do f following f, right? That's always right. So f squared, oops, using black, f squared of x, 3x plus 1 over x plus 2, is f following f of x is equal to f, of f of x is equal to, so this is going to be over 3x plus 1 over x plus 2 plus 1, like that. All right? So, right, because f of x is 3x plus 1 over x plus 2. I guess I skipped the step in there. So this is equal to what now? 9x plus 3 plus x plus 2 over 3x plus 1 plus x plus 2, which is equal to 10x plus 5 over 4x plus 3. Has anybody taken matrix algebra yet, or elementary linear algebra, or differential equations with matrix algebra? Has anyone taken one of those classes yet?
Yes.
All right. Does do you see something kind of? Right. I mean, if you look at this type of function, a linear function divided by a linear function called the rational function, those actually they correspond to 2 by 2 matrices. So 3, 1, 1, 2. If you do this matrix multiplication, what do you get? 3 plus 1, or sorry, 3 plus 3. Oh no, it doesn't correspond in this way. I thought it did. No, it does. No, 3 times 3 is 9 plus 1 is 10. And then 3 plus 2 is 5. 3 plus 1, no, 3 plus 2 is 5. 3 plus 2 is 5. Did I make a mistake here? Oh, that's a 2. That's 2x plus 2. So 5x plus 3. And no, that's a 4. Plus 5. There we go. And then in the last row, last column, 1 plus 4 is 5. All right, so this 3x plus 1 over x plus 2 corresponds to the matrix 3, 1, 1, 2. And then when you square it, you get the matrix corresponding to this. So functions of that form, ax plus b over cx plus d, they correspond to 2 by 2 matrices like that, as long as they're not multiples of each other, the two rows. And then composition corresponds to matrix multiplication. It's pretty cool. A nice connection between matrices and rational functions there. And the geometric properties of those types of functions, when you look at them over the imaginary numbers, is even more interesting. But that's just a side note. All right, here's a couple of properties of composition. So consider f from A to B and G from B to C. Prove that if f and G are 1, 2, 1, then G following f is 1, 2, 1. All right. Well, how does the proof for that one start? How does one prove a function is 1 to 1? What does one have to show?
So each element in the domain goes to one element in the range?
Yeah, how do you encode that in terms of functions? Yes, that's correct. Now, how do we encode that property? So you suppose that, or assume that, I guess we've been using the word assume, right? So assume that GF of, well, GF of P is equal to GF of Q. Right, and we need to show that what? Oh, I'm sorry.
Sorry, you just reconnected. Could you ask that again?
Oh, so we assume this is true. Now, what do we need to show? Actually, we need to assume something else to start with. Assume that G and F are 1, 2, 1. Now, assume that this is true. All right. Now we need to show what is true. Right, you want that every two elements in the domain go to, sorry, no two elements in the domain go to the same thing in the range. So given that, P and Q go to the same thing in the range, you want what to be true? That P and Q are
Equal.
equal, right? We need to show that P and Q are equal. All right. So assume that this is the case. So by definition, well, GF of P is G of F of P, and this is G of F of Q. And now because G is what? What is G? What do we know about G? What do we know about G? What do we assume about G?
It's 1 to 1.
Because G is 1, 2, 1, we get what? Right, so G of this thing and G of that thing are the same. Therefore, what must be the case? Right, we have G of this is equal to G of that. And because G of 1 is 1 to 1,
This is equal to that.
this is equal to that. All right, what is this and that in this case?
F of P and F of Q.
Yeah, F of P, this is equal to that. And now because well, next step. What are we working towards? We're working towards P equal to Q. Well, we managed to
F 1 to 1.
yeah, because F is 1 to 1. What?
P is equal to Q.
P equals Q. As required. Period. All right, so compositions of injective or one-to-one functions give you one-to-one functions. Same deal with surjective functions. So, same example. So consider F from A to B, prove that if F A to B and G from B to C are, so I really don't like the word onto, using it as an adjective. So we'll just say surjective here. So if F and G are
You're-
surjective, then G following F is surjective. Okay, so proof. All right, so GF, remember, is a function, so maybe it would be good to write it this way, is surjective. All right, so F goes from A to B, G goes from B to C, and so G following F goes from A to C. So assume that F and G are surjective. Now, let what? So now we need to show that G following F is surjective. So what do? We pick an element of the range of who? And we need to pick an element of the range. So we want to show that this function is surjective. So we need to pick an element of its range. An arbitrary element of its range. So let Z be an element of C. Now we need to find, so we took Z right here. Now we need to find X in A such that G following F of X is equal to Z. Alright, so let's look at a picture here. Maybe it'll be helpful. So here's A, B, C. Proofs don't have to have pictures, but sometimes they're nice. Sometimes they definitely are appropriate. I'm one who likes pictures and proofs, but when you're learning how to write proofs, sometimes it's. I mean, we haven't drawn too many pictures here because we're not talking about things that are necessarily pictorial. But I mean, sometimes they help. I'm definitely a big fan of them in my own work. All right, so we have Z and C. We want to find X and A. So that's a G following F of X is equal to Z. Well, what do we know? Okay, what do we know? We know G is surjective. Because G is surjective, so G goes from B to C. Is surjective what? Come on, guys. Because G is surjective, what? There is Z is in the range of G, and G is surjective. Z is in the range of G, and G is surjective. So what must exist?
Every range element has an in arrow.
Yeah, okay. So how do we encode that in the language of functions? Right? There is an in arrow. In other words, there is something where?
There is an X for an element of A.
A? G
Or
is
B.
surjective. G goes from B to C.
There's an element of B,
What should we call it?
Y.
There's Y in B such that what?
F of y equals z.
F or which? G of Y.
G.
G of Y is equal to Z. All right. Next, because F is surjective, there is what? So Y is in the, show me right F. From A to B is surjective. Because Y is in B, which is the range of F, there's got to be an in arrow going to Y. So there has to be what?
There is an X that's an element of A such that f of x equals y.
Fx equals Y. So now Z, which is equal to G of Y, and Y is equal to F of X. Well, G of F of X is what? Oops. G of F of X is the definition of what? That's the definition of G following F of X as required. Alright, so given the Z, there's a Y here. Given the Z and C, there is a Y and B, such that G of Y is Z. And that's because G is surjective. Because F is surjective, given the Y and B, there is X and A, such that F of X is equal to Y. So, that means Z, which is G of Y, is G of F of X, which is G following F of X. So, there's a bit of a disconnect between the idea of the in arrows, the intuitive idea of the in arrows, and the notation or language of functions. Notation in mathematics is critical. Correct notation needs to be used because that's how you communicate the ideas. So there's an interplay between, there's disconnect between intuition and notation. Okay, the intuition is what guides you, but then it needs to be put into notational form at the end, and that's a leap. That is a leap at times doing that. If I didn't give you a homework on function compositions in this chapter, but we will do it later. So I would do these proofs on your own. These two here, they're good examples. But finish the homework before you get into that. All right. So I want to start chapter 5 in the last 15 minutes here. And I will have an assignment for you for chapter 5 on Friday. Chapter 5 is a little bit shorter than chapter 4. So chapter 5 is on relations. So the definition of a relation. Given a set A relation on A is just a subset, well, not just, I shouldn't say that in a definition, is a subset of the Cartesian product of A with A. That's all it is. That's the basic definition. But this is not the notation that's used when talking about relations. Okay, there's lots of different notations that are used, but when talking about when discussing relations, the following notation is used. Okay, so and there's different symbols that are used, but the most abstract symbol is this twiddle or tilde. Let tilde be a relation on A. Okay, so we say let tilde be a relation on A, and then when x, y is an element of that relation, we write x twiddle y instead, x tilde y. So that's one symbol that's used. Other symbols that are used for relations, are as follows. Aside from tilde are a right-facing arrow, this symbol, this symbol, this symbol, or this symbol. Now, all of those symbols have meanings attached to them that you have encountered at some point in time. But they meaning of them may change, okay, or it may have a special meaning. I mean, when you write this to stand for a relation, don't think that it means less than in the sense of real numbers, like 3 is less than 5, or 4.999 is less than 5. Okay, it may mean something entirely different that's sort of related to the notion of less than. Other symbol, what am I missing? Oh yeah, also the subset symbols, etc. Okay, the meanings of these symbols may be the traditional meanings, or some other meaning that will be explicitly mentioned. Okay, so for example, lots of examples. Okay, given a set A, well, given the real numbers, right, this less than or equal to with its usual meaning, given the real numbers are, this with its usual meaning is a relation on R, right? 3 is less than or equal to 5. 5 is less than or equal to 5. 6 is not less than or equal to 5, etc., etc. So the usual meaning of that. By the way, also, if x is less than or equal to y, and y is less than or equal to x in R, then what? If you write x is less than or equal to y, and y is less than or equal to x, for that relation, that standard relation of less than or equal to in R, then what must actually be the case?
X equals
And
Y.
actually x equals y. In other words, this less than or equal to relation is not symmetric. Right? The only time x is less than or equal to y and y is less than or equal to x when they're actually the same thing. Right? I mean, or if you use strict inequality, if x is less than y and y is less than x, well, that's impossible. Right? So you never have like 3 is less than 5 and 5 is less than 3. Other relations are symmetric. Given the set Z, let this be a relation on Z where x is related to y when x minus y is, x plus y is even. So when the sum of the two numbers is even. Right? So for example, 3 is related to 5 because 3 plus 5 is 8, which is even. 5 is related to 3 because 5 plus 3 is 8. So in this case, or also 7 is not related to 2 because 7 plus 2 is odd. In this case, if x is So for this relation, x is related to y if and only if y is related to x. So with this type of relation, with this relation that I'm defining here, it is symmetric. Whenever you have x is related to y, y has to be related to x as well. Other relations are not symmetric. Just because you got x related to y doesn't mean y has to be related to x. Okay, so those are two kind of standard examples of definitions, or standard examples of relations. Okay, now relations in their just sort of abstract form are not that interesting. Putting conditions on the relations and classifying those different types of conditions, that is something that is more interesting and something that is used. So a certain special type of relation is called an equivalence relation. So a relation tilde is an equivalence relation when it satisfies the following a relation this on set A. Is an equivalence relation when it satisfies the following three properties. Reflexivity, the reflexive property, for all x in A, x is related to x. Symmetric, for all x and y in A, x related to y implies y is related to x. Transitive, for every x, y, and z in A, for every x, y, and z in A, x related to y and y related to z implies x is related to z. So the three properties on a relation, if they're satisfied, it gives you what's called an equivalence relation. So, for example, that relation about the sum being even, that is an equivalence relation. So, recall the relation on z given by x is related to y when x plus y is even. Let's show that this is an equivalence relation. Okay, first we have to show that it is reflexive. So reflexive. All right. Let x be an element of z. Okay, what does it mean for x to be related to x? What would it mean for x to be related to x? What does it mean in terms of things we know about? It would mean what? that oops, x related to y, x is related to y when x plus y is even. All right, so what would it mean for x to be related to x? What would it mean for x to be related to x?
Is it x is an integer?
Yeah, x is an integer. What does it mean for x to be related to x? The definition of the relation is right here.
Would it be that it's even also?
Nope. X is related to y when x plus y is even. So, what does x related to x mean?
X plus X is even?
Right. Well, x plus x is equal to 2x, which is that even?
Yeah,
Yeah.
that makes sense.
Yeah, which is even. Therefore, x is related to x. The reflexive part is often not difficult, but it still needs to be said. Symmetric. All right, so what is the meaning of symmetric? For every x and y in A, x related to y implies y is related to x. So, in order to show symmetry, you take x and y in A and assume x is related to y. Take x and y in A and assume x is related to y. Then show that y is forced to be related to x as well. Okay, so take x and y in Z and assume that x is related to y. This means that well, if we assume that x is related to y, it means that what in this example?
X plus y is even.
No, x plus y is even. Well, since x plus y is equal to y plus x, we now get that what? So x plus y is even. So therefore y plus
Y
x is even.
related to X.
Y is related to x as required. So reflexive, symmetric, transitive. Oh, it's time to go. Take x, y, and z in the integers and assume that x is related to y and y is related to z. Therefore, X plus y is even, and y plus z is even. And what does even mean? This means x plus y over 2 and y plus z over 2 are both integers. All right, you can think of even, an integer being even, as when you divide that integer by 2, you get another integer. Right? You don't, not like 3. 3 over 2 is not an integer. It's 1.5 or whatnot, whole number. Okay, so now x plus y over 2 and y plus z over 2. Well, this is going to take just a little bit of time to, it's fine. Sorry, x. Okay, we got to go. We'll finish this next time. Okay, guys. So email me with questions if you have them. And any other concerns, okay? And other than that, we'll see you on Friday. Okay, have a nice afternoon, everyone.